What up, what up? Check, check. Can everyone hear me? Can everyone see me? That's a good question. What is going on, everyone? Happy Tuesday, and welcome to an Integration Bee. Would you do a U-sub? Yes, I think a lot of the problems that we're going to do today is going to require some U-sub. Oh, I think you're referring to this problem. Maybe that is a possibility. That is a problem that we will do later on, but I kind of wanted to, get a little conversation started on with this problem, but we will review it soon. Or would you like for me to start off with that one? Let me know in the chat if we should do this particular integral problem that is on the screen, or if I should do another one. I guess let's just start off with this. Let me go ahead and write it on my Blackboard, and then I'll remove everything else. Okay, up to you. You know what? I am deciding that we should do it just because you started asking a question about this, and I think we should definitely do that. All right, guys, just so you know, let me go ahead and show my Blackboard here. Hopefully everyone can see this now. Just so you know, we are like 500 followers away from being to 20K. So if you like, please like this video, like the live, follow me on Instagram, follow me on TikTok, subscribe to my YouTube channel. But today, every Tuesday at 3 p.m. or around 3 p.m., we do some Integration Bee practice. Keith said, will you discuss basic integration? I think on Thursday, we're going to do some basic integration. So we're going to do some like U substitution, very surface level. We'll do some integration by parts. We'll talk about the power rule. But typically Tuesdays are going to be a lot for more complicated problems. So really, it's up to you. You just, follow along and try to learn different tricks that we do here. But it's always good to chat and, discuss different methods. So we're going to go ahead and start solving this integral. And John had mentioned that we're going to do U sub. And I think we are going to do U sub. But the very first thing that we want to do is we want to kind of get rid of that radical or that radical expression. As you can see, we have something on the top, something on the bottom. So we're going to multiply both the top and the bottom by the conjugate. Let me go ahead and start writing that down. And what I mean by the conjugate, it's going to be this root x plus root 1 minus x, and then root x plus root 1 minus x. I'm doing that to the top and the bottom. And the reason why I'm doing that is so the bottom doesn't have any radicals. I don't know if this is going to lead us anywhere, but I think that's going to be the case. All right, so let's go ahead and continue. Let's work on the top first. On the top, what you're technically doing is a FOIL of these things. So if you follow along, if I start with the first and then I start with the last, or the outer, if you will, we're going to be left with x plus root x root 1 minus x. And then we're going to do the inner and the last. And that's going to be plus root x root 1 minus x plus 1 minus x. You're going to see that those radicals cancel out. And in the bottom, let's go ahead and do that. So we're going to go ahead and do the first, the outer. So we're going to start off with x plus root x root 1 minus x. And then we're going to do the inner and the last. And that's going to be minus root x root 1 minus x minus 1 minus x. So on the first term and the last term, when I multiply those together, because there's the same value, those radicals are going to cancel out. So let's talk about the top. It looks like we have some common values that we can go ahead and simplify. So I still have, on the top, I have x plus 2 root x root 1 minus x, and then plus 1 minus x, all over. On the bottom, you're going to see that the roots cancel out, which is really nice. Users, yes, you're off duty. You know what? We're here to have fun. It is Tuesday. This is what we do every Tuesday at 3 p.m. Okay, stargazing. I will do that integral right after this problem, okay? Sine of root x. So hang on there. Okay, so let's continue, guys. On the bottom, you're going to see that the x's, this x, and actually those don't cancel out, this x. And if I distribute the negative sign on the bottom, I'm going to be left with x minus 1 plus x. So now let's go ahead and simplify more stuff. And it looks like I'm forgetting my dx. All right, so now we have 2x plus 1. And on the top, those x's cancel out. There's one x here, and that subtracts. So we are just left with 2 root x root 1 minus x plus 1 all over. Check this out. The x's have like terms, so this just becomes 2x. And I believe that should have been a 2x. Somehow I feel like that should have been a 2x plus 1. What a burner. Let me just make sure that I actually wrote this problem correctly. Sometimes I write it down on the screen and I totally forget what I wrote, but it should be 1 minus x. No, it looks like that is correct. Oh, so the thing that I messed up on for the specific integral should be 2x minus 1, not 2x plus 1. That'll make it way more complicated. Let me erase that now. And you're going to see why it's important to do that. So minus 1, minus 1, minus 1, minus 1. Okay, so now in the denominator, you're going to see that we have 2x minus 1 because look at that. The 2x minus 1 and the 2x minus 1 is going to cancel out. And so now what we have is we have integral of 2 root x root 1 minus x plus 1 dx. Not bad, right? Okay, so let's go ahead and create some space on the blackboard here. And then we can go ahead and continue integrating this. Whoops. How was everyone's weekend, by the way? I was on YouTube Live on Monday. Was talking to some people from Brazil, some people from London. I'm curious where y'all are from. Okay, here we go. So let's continue. This integral, if we simplify it, if we multiply those radicals together, just give me 1 second. Looks like my iPad wants to give up on me. This is going to be integral, 2, and then I'm going to go ahead and multiply that x into the other radical. So this is going to be x minus x squared, and then we have plus 1 dx. It was a short weekend, that's true. I think a lot of people have been having like 3-day weekends, some 4-day weekends, so definitely short, but hopefully it was nice. All right, we have two things being added together. Let's go ahead and just separate these two. So that second integral, the integral of 1 is just going to be x. We're not going to really worry too much about that. What we're going to focus on is that root 2, or 2 root x minus x squared. So let's go ahead and rewrite it. This is a 2, and then I have negative x squared plus x plus root or integral 1 dx. Can anyone tell me in the chat what you guys think I'm about to do with that last radical that we have, that first integral? I'm definitely going to do something to it. I'm curious what you guys think. Yes, John, I 100% agree. Maybe on a Thursday I can do that. Okay, so MM said pull out the 2. Why don't we do that? I think that'll be great. Because now what we have is we have 2 integral root negative x squared plus x, and then we still have, you know what? For that last part, I'm still going to leave that integral there so we don't forget that that's what we're doing. All right, so I pulled the 2 out. Anything else? Any suggestions on what we can do? Factor out the GCF. You know what, John? If we factor out the GCF, just notice that we're going to end up with one of the previous steps. It's basically this step that I'm going to circle in red. If we factor out a GCF, we're just left with that root x times root 1 minus x. So we're going to do one of my least favorite problems, or my least favorite methods here. We're going to go ahead and complete the square. Okay? So we still have the 2 on the outside. And inside, I'm going to factor out a negative. I guess maybe that's what John was talking about. Factor out a negative from here. So I have x squared minus x. And now I'm going to go ahead and complete that square. The CTS, yes. Okay, how do we complete the square? We're going to go ahead and take the b value, which is a negative 1, divided by 2 and square it. And that becomes 1/4. So technically what I'm doing is I am going to introduce that 1/4 on the inside of the parentheses. But then I have to make sure that I do the opposite of that right outside of it. Now, I'm not going to subtract a 1/4. I'm actually going to add a 1/4 because if you notice, we still have the negative sign outside the parentheses. So really what I introduced was a negative 1/4. So back to that minus 1/4 that I had inside the radical, I'm just going to turn it into a plus 1/4. Okay. And then don't forget, we still have that plus root dx. And then now what we have, let me just rewrite some stuff. The 1/4 is going to go in the front, minus x minus 1/2 squared. And this is dx plus root dx. Aha, hopefully you guys can see that last radical that I have. What do you think that's going to become? Do you guys have any idea of how we can solve that? There's a few methods that we can use, but I'm curious what you guys think. Let me know in the chat what you guys think I should go ahead and do. I'm going to go ahead and use trig sub, but I'm not going to do use substitution. I just feel like that's just too much work. Yes, Preston said it's going to be an arcsin, and I think so too, or it might be a trig sub problem. I don't really know what that's going to be. Ooh, Mateo said difference of perfect squares. Now, you could try that, but because this is in a radical, because it's in a square root, it might prove a little bit more difficult. If you notice, this is a very, very typical trig sub problem. And so how that's going to work is like this. I'm going to set up my triangle. So I have my theta. My hypotenuse is going to be 1/2. You're going to see why. And then my opposite is going to be x minus 1/2. And so what we have now is we have sine theta is equal to x minus 1/2 over 1/2. If I multiply the 1/2 to the other side, I have 1/2 sine theta is equal to x minus 1/2. And I can go ahead and take the derivative of that. So 1/2 cosine theta d theta is equal to just dx. That's going to help us for our trig sub. Okay? But we just need to figure out what that radical is. Well, looking back at the triangle, you can see that if we used Pythagorean theorem, we would get that this opposite value, or the adjacent side, I'm sorry, is going to be 1/4 minus x minus 1/2 squared. And so what we can say is that cosine of theta, looking at the triangle, is adjacent over hypotenuse. So it's 1/4 minus root, or x minus 1/2 squared, all over 1/2. So if we multiply the 1/2 to the other side, we have 1/2 cosine theta is equal to that, all that root, that entire root value that we had. And this is perfect, guys, because now we can go ahead and rewrite our integral, because we know that that entire root value is going to be the cosine. We're going to go ahead and do that. We're going to have 2. Whoops. So we still have 2 on the outside. Integral of, instead of the root value, we're going to do 1/2 cosine theta. And then times our dx. Do not forget that our dx was here. I'm circling that in red. So now what we're going to have is 1/2 cosine theta. And then d theta. And then, of course, we still have the integral of dx, which is just going to be x. Okay, let's go ahead and simplify this. I can multiply the 1/2 on the 1/2. That's 1/4. But when you pull it on the outside, I have 1/2 integral of cosine squared theta, d theta, plus integral of x. All right, who can tell me how we can solve that first integral, cosine squared theta? Anyone have an idea what we can do? We can definitely do something. Does anyone remember the half angle formula? I'll write it down right underneath. Remember that cosine squared theta is equal to 1 plus cosine of 2 theta all over 2. So we can rewrite that integral using the half angle formula. So we have 1/2, 1 plus cosine of 2 theta all over 2 d theta plus integral of dx. All right, guys, we're about to be done with this one. I had this problem in the very beginning of the screen just as like a conversation starter, but it seemed like that's kind of what people wanted to run with. I believe there was one person in the beginning of the chat that wanted to do this problem. So, or they said I can do whatever I wanted, but because it was already on the screen, that's what we're going to do. All right, so let's go ahead and pull that 2 that's on the bottom out. So we have 1/4 integral of 1 plus cosine of 2 theta d theta plus, I'm just going to go ahead and take the integral of that last one. That's just going to be x. And so now we have 1/2 times theta plus sine of 2 theta over 2. I basically did a u sub there. I just didn't want to do all the work. And then we have plus x and then plus c. So this is 1/4 theta plus sine of 2 theta over 2 plus x plus c. And that is going to be the solution to this. One thing that we will do is we will go back to the our triangle. And in the very beginning, if you recall, sine theta was equal to x minus 1/2 over 1/2. So if we take the arc sine, we're going to get x minus 1/2 over 1/2. And that is the entire arc sine of that. So you can plug it back into your theta, and then sine 2 theta you can rewrite as 2 cosine theta sine theta. But I think everyone had enough of this problem. We can go ahead and go to the next one. But I believe Preston was in the very beginning. He said this is going to be an arc sine, so that's exactly what this was, or a derivative of an arc sine type thing. Okay, so let me go ahead and erase this. And now we can go ahead and do someone, I believe. Yes, John, you're absolutely right. All right, have a good one. We'll see you soon. Okay, so Stargazing, I believe, had requested this integral. And it's not too difficult, at least I don't think. So it was sine of root x dx. Okay, so looking at the chat, I'm curious, chat, what would you guys like to do? What should be the very first thing we should try? Any suggestions? What do we think, guys? Let's do a u sub. Yusef said u sub. That is 100% correct. So u is going to equal to root x dx. Oh, not u is equal to root x dx. U is equal to root x. Okay, so check this out, Brady. We're going to take the derivative of this. 1 over 2 root x is dx. And then we're going to go ahead and multiply the 2 root x to the other side. And now we have 2 root x du is equal to dx. And so let's go ahead and plug that into our integral. And now we have integral of sine of u times the dx, which is 2 root x du. Let me clean this up a little bit. You know what? Not today, but I think that's a good time to do something like that, anime lover. I agree. I'll definitely take a note of it. Okay, so if I rewrite this, this becomes sine of u and then root x du. And I believe Brady said, we're going to do u sub, but I don't know what to do from here. Well, check this out, guys. We have the root x in our integral here that has everything in terms of u, but we know what that value is. That is what our u is. So we can go ahead and write that. So now we have 2 integral of u, I just put it on the outside, sine of u du. Yes, solve for x in terms of u. Yusuf, absolutely right. And then from here, this is going to be a simple integration by parts problem. So if we use our integration by parts problem, I'm going to use w as my u. My dw is just du. My dv is going to be my sine u. And then my v is going to be negative cosine u. And so now we have this beautiful integral 2 times negative u cosine of u minus integral of negative cosine of u du. All right, let me go ahead and create more space on the blackboard. I'll clean this up a little bit. But as you can see, we are almost going to be done. So Stargazing, if you're still here, hopefully this makes sense to you. But this was the request that you made. So now we have 2 negative cosine of u. I'm going to clean this part up because we have 2 negatives in front of that. Well, we have a negative and then a negative cosine right inside the integral. I'm just going to put a plus integral of cosine u du. And now let's go ahead and finish this off by integrating. So I'm going to distribute the 2 at the same time. And so now we have 2 or negative 2 cosine of u plus sine of u plus c. And we're not done yet because don't forget that our u value has to be root x. So then our final answer is going to be negative 2 root x cosine of root x plus sine of root x plus c. That's it, guys. Oh, Brady. Oh, Brady, I'm going to show that integral there. I believe this is, I don't typically like these, but I'm just going to show you the integral that Brady's referring to. It's integral from negative infinity to infinity of 3x e to the 4x squared. Which I don't think is that bad, but I believe this is the Gaussian integral where negative infinity to infinity of e to the x squared is equal to, what was it? I think it's like root pi or root pi over 2. I always forget it. But that one's like no fun. I mean, you can use some Feynman techniques for that, but to be honest, it's just like it's once you know that integral, once you can mask it as that, then it's going to be pretty simple to solve. But we can definitely talk about that one just because it kind of goes off the rails. I want to talk about that one on Friday. I'm going to take note of it because I do have something similar to that I've been wanting to talk about on Friday. But today, I'm just going to stick to the game plan that I have here, okay? All right, let's go ahead and do something that I think most people are going to truly understand. I have the integral of x over root x squared minus 3. I'll remember you, Brady. I would definitely write it down. Okay, looking at this problem, what does everyone think? What can we do? Let's do a u sub, okay? This one's going to be pretty simple in my opinion. Starts off as u is equal to x squared minus 3. Du is a simple 2x dx. And so du over 2x is equal to dx. And now we can go ahead and rewrite our integral all in terms of u. So we have integral of x over root u times du over 2x. Okay, the x's cancel out. And we could bring out the 2 out on the front. And we have 1/2 integral of du over root u. All right, what can we do next? Because it looks like we just have the root on the bottom. Can't really do stuff yet, or at least I can't do the power rule. Yeah, Brady said power rule, but what's interesting about this is that the root's on the bottom. All I'm going to have to do is just rewrite it. So we have 1/2 integral of u to the negative 1/2 du. And then, yes, Brady, nice job, negative exponent. That's exactly what it is. So now all we have to do is watch out when you add these fractions. It's going to be 1/2 u to the, I have to add 1 to the power, which is going to become 1/2 divided by 1/2. Because I added 1 to the power, it became 1/2, and I add by, or I divide by the new power. What's up, user 851709? And so don't forget your plus c. So this is literally just going to become root or u to the 1/2 plus c. And don't forget that u was that value, x squared minus 3. So what we have is root x squared minus 3 plus c. Okay, pretty harmless, right? Now, let's just flip these things around. So we have root x over root x squared minus 3. But then what happens when you have this, guys? Root x squared minus 3 over x. Yusuf, to be honest, I feel like integrals are nice little puzzles. And it's been proven that the more videos I make of these, the more people like them. So they're just fun. I love watching, people solve them online. And I love watching Integration Bee videos. And I think they're just, they're super fundamental, and it really tests your algebraic skills. Square root 169. I see you. What up, dude? Oh, thanks. Yeah, I hope you're enjoying them. Hopefully, I'll come up with some new ones. I'm trying to do like 1,000 algebraic problems for like algebra students, and I really want to do some like tough integration problems. Even though I have one already, I feel like they can be more difficult. Oh, Gabriella, thank you. Yes, I'm glad you are. But I'm still curious, guys. Chat, what do you think we can do? Should we start doing use substitution? Do we think it'll work? Again, this is just a little different from the other problem that we just did. Let's just try use substitution. Let's see if this is going to work. I already said it isn't, but I'm going to show you why that's the case. So if you make u equal x squared minus 3, du is equal to 2x dx. And then we're going to go ahead and divide the 2x to the other side. Du over 2x is equal to dx. And so now we have integral of root u over x times du over 2x. And this becomes root u over 2x squared du. Okay, so Brady said u sub and then rewrite x squared in terms of u. Okay, nice. Yeah, I think it's just funny to explore calc once in a while, or to get in there and just try some math problems. Honestly, they're really fun. Read as many examples as you can, and I think you'll have a good time. I think it's just a good exercise for the brain. Okay, so Brady said we're going to go ahead and rewrite this. And I guess what we can do is, since the beginning u was equal to x squared minus 3, we're going to go ahead and add the 3 to the other side and get u plus 3 is equal to x squared. But check out what happens. On my new integral, I have 1/2 integral of root u over u plus 3 du. Yo! What do you think of this? Is this doable? Should we try something else? Any suggestions, chat? What do you think? Yeah, you see how it doesn't work? We're kind of left with a different problem. And I don't even know how I would go about solving this. So we're definitely going to have to do some rewriting. We're going to have to start this all over. And again, just because I flipped those values on the top and the bottom, we are going to have to revisit this and do, you guessed it, trig sub. Yes, we are going to do some trig sub. These are the ones when I was in high school I was really worried about, just because I didn't quite understand the whole triangle thing. But the more you do them, the better it becomes. And again, just messing around with it, like I was telling Yusuf, continue messing around with as many problems as you can, and you continue to get much, much better at them. Okay, so let's go ahead and write our triangle here, since we're going to do trig sub. There's my theta. Sub, trig sub, light work. That's right, Max. That is right. Okay. So let's go ahead and make our hypotenuse our x, and then we're going to make our opposite, it's going to be root 3. Ooh, don't like that, but oh well. And if we do some Pythagorean theorem, this bottom value will be x squared minus 3. Okay, so now we have to go ahead and figure out some stuff. We can say that sine theta is equal to opposite of our hypotenuse, so root 3 over x. In other words, because the x is in the bottom, it's a little tricky. In other words, I can say cosecant is equal to x over root 3. And so that means that root 3 cosecant theta is equal to x, and now I can go ahead and integrate this. Now, what is the integral of cosecant? That's something that you have to remember. That's going to be negative root 3 cosecant theta, cotangent theta, d theta, and that's equal to dx. Yusuf, how do you know the triangle values? So from experience, seeing how we have an x squared minus 3, I made the x the hypotenuse, because with Pythagorean theorem, you're going to have to do x squared minus 3. And also, again, so you always have to take the square root of x squared, for example, and that's just x. So that's going to be one of the triangle sides. For the 3, if you take the square root of 3, that's going to be root 3. Because when you do Pythagorean theorem, let me write this in red. If you do, a squared plus root 3 squared is equal to x squared, then this is a squared plus 3 is equal to x squared. And as you can see, x squared minus 3 is that a squared value. So when I take the square root of that, I get the x squared minus 3 that I desire. So again, it's all about just messing around with this. Some people have shortcuts and they say, oh, when it looks like this, just use secant. I don't like to remember them. I honestly just like to draw them out. It's much easier for me. But anyway, this is going to prove helpful because now what we're going to do, okay, we just need to find how to rewrite this, the root x squared minus 3. And what we're going to use is we are going to say that looks like cotangent of theta is equal to root x squared minus 3 over root 3, meaning that root 3 cotangent squared is equal to root x squared minus 3. And that's going to help us a lot because now what we're going to have is we're going to have the integral of that root value is our root 3 cotangent. So we have root 3 cotangent theta times, what's our dx? It is this value, the negative root 3 cosecant cotangent. So we're going to have times negative root 3 cosecant theta, cotangent theta, d theta. And then the whole thing has to be over x. Now, what is x? It is going to be this value that I'm going to circle in red. It is the root 3 cosecant. And so now what we have is we have root 3 cosecant theta. And as you can see, a few things are going to cancel out. The root 3 cosecant cancels out with the root 3 cosecant that we have on top. And so what we have for our new integral is going to be negative root 3 on the outside, and then we have cotangent squared theta d theta. Nice. Varies, why not u sub? We tried it and it didn't work because it was a little tricky, but if you worked it out, and I did it in the previous video or like just a few minutes ago, and by the way, I do record these and I will put them on YouTube for you guys to watch later on, but we tried it out and the u sub just didn't work out, so we had to use trig sub. Okay, so going back to this, guys, cotangent squared, does anyone remember what that simplifies to? Cotangent squared, could we integrate that or do we have to rewrite it? I'm looking specifically for a Pythagorean identity. Right on. This is cool. Well, listen, you continue looking at these videos, you continue looking at these methods, and it's okay if you're a newbie. We're all newbies at some point. We just look at methods, and when you do see it for the first time, you're going to be like, oh my goodness, I saw this on TikTok. Okay, I'm looking for if anyone knows the identity for cotangent squared or the integral for cotangent squared. I honestly can't remember the identity for cotangent. It's definitely one of the Pythagorean identities. Cotangent squared. So that is going to be cosecant squared minus 1. 1 over x squared plus 1. Huh. So this is actually going to be the derivative of... This is the derivative... No, it's going to be this. Negative root 3... integral of 1 minus, is it 1 minus cosecant? No, it's cosecant squared minus 1, my bad. So now we're going to have cosecant squared theta minus 1 d theta. Nice, nice. We'll do a partial fractions problem after this. All right, so now we just got to go ahead and take the derivative of this. Do we know what the derivative of this is going to be? That cosecant squared is literally just going to be a negative cotangent. So now what we're going to have is negative root 3 times negative cotangent theta plus, I guess we can say a root 3 theta, and then plus c. Okay, and then from here, let's just go ahead and make things a little smaller. And we are going to go ahead and just simplify and put everything back into the problems that we needed. Whoops, it looks like I shrunk this. Did not want this. Give me 1 second. There you go. Much better. Okay, so we're going to make our work a little smaller. And then we're going to finish this off. Okay, so it looks like our answer is going to be root 3 cotangent theta plus 3 theta plus c. So let's go back to our integral. Cotangent, or our triangle, cotangent is going to be adjacent over hypotenuse, or adjacent over opposite. I'm sorry. So then what we're going to have is we're going to have root 3, and the adjacent was literally just root 3. Whoops, the adjacent was root x squared minus 3 over root 3. And then plus our theta, we can find out by using the, we can do the sine, for example. We can say theta is equal to sine inverse of root 3 over x. So we can go ahead and plug that in. So that's just going to be 3 sine inverse of root 3 over x plus c. There we go, guys. All right. So let's go ahead and do another one. We got plenty of time. Let's see. I'm looking at Swanson said that they just learned trig subs and partial fraction integrals. I think it's time we can do like a partial fraction integral. That's for sure. Okay, so let's go ahead and try one out. Let's do by the way, speaking of partial fractions, let's go ahead and do this one. X minus 4, whoops, x minus 4 over x squared plus 2x minus 15 dx. All right. As you guys look at this problem and try to think of what method we can use, I just want to say that I think I found a interesting solution to this integral here. 1 over x to the 5th plus 1. It's been bothering me so much, but I feel like I have a nice way of showing this. It's a little, I think it's nice. It involves some imaginary numbers, but I think it works. But we'll see. I'm really curious if it works out. I'm going to try it out. It's just, it takes some time to write all the details, but looking forward to talking about that. Okay, so various to long division. Think about it, okay? If we try long division, the only way that's going to work is if the degree of the top is either the same or more than the bottom. Meaning that because the degree of the bottom is 2, the top either has to be 2, 3, 4, and beyond. So we can't really use long division here. But we are going to go ahead and use partial fractions. So we're going to go ahead and simplify the bottom by just factoring it. That's going to be our first step. So we're going to do integral of x minus 4 all over x plus 5, whoops, times x minus 3. Yeah, if they were flipped, you could, absolutely. All right, so again, every time we use long division, the degree of the top has to be the same or more than the bottom. But look at this. This is in honor of Swanson, who's just learning partial integrals. Now we have to go ahead and separate this using partial fractions. So this is supposedly going to equal to some value a over x plus 5 plus b over x minus 3. And then now we can go ahead and rewrite some stuff. So now we have a times x minus 3 plus b times x plus 5. So if you guys remember, partial fractions, that's the way we set it up. And Gabriella, yes, you can easily do synthetic division. Obviously, it has to be, or it's best if the bottom, that stuff we're dividing by, is just a binomial. So like x minus 1, x plus 2, it has to be that easy. Otherwise, unfortunately, we do have to use long division. But synthetic division is just a nice shortcut for long division. Okay, so this whole thing should be equal to our actual numerator in the function. This should equal to x minus 4. Okay, so now a lot of people, they use, I think it's called like the hidden method or something like that. I think it's proven useful in this case. The way they do this is they look at each parentheses and they say, hey, if I made x equal to 3, then what would happen if I plugged that 3 in for every value of x? We would get a times 3 minus 3 plus b times 3 plus 5 is equal to 3 minus 4. Okay, I kind of want to prove or like show the whole work here. You're welcome, Gabriella. Yeah, that's what we're here for. So the reason why I plugged in 3 is because look at that first parentheses. 3 minus 3 is 0. That's really nice because that eliminates our a value. So then all we have is 8b is equal to negative 1. So b is equal to negative 1/8. And then now we're going to do the same thing, but now we want to eliminate the b value. So if we look at the parentheses that's in front of the b, it's an x plus 5. So we're just going to make x equal to negative 5. So we're going to start all over again, but this time we're going to make x equal to negative 5. So that we have a times negative 5 minus 3 plus b times negative 5 plus 5 is equal to negative 5 minus 4. So check that out. For that b value, everything is going to go away, which is really nice. That cancels out. So then now all we have is negative 8a is equal to negative 9. So a is equal to 9/8. And then now we're going to have this amazing integral. We have the original one. And then so if we're using partial fractions, this is going to become integral of 9/8 over x plus 5 dx plus 1/8 over x minus 3 dx. You're welcome. Yes, partial fractions are proven to be very useful. Again, this is all about just having fun, learning different methods, seeing little tricks. Okay, I'm going to kind of make this smaller so that we can finish off our problem. But start thinking about what that first solution is going to be, that first integral, 9/8 over x plus 5. Yeah, how do you hide the chat? I don't know. I think there's like some settings to it, but I don't really know. Hopefully someone in the chat can see this. Yes, Gabriella, this is exactly what's going to happen in a calculus class. This is, this could be more advanced. This is like calculus AB. Some people, or calculus BC would definitely see this, but this is like a fundamental method that a lot of people use. Okay, so hold down. So Samantha's saying hold down, and then that's it. Oh, there you go. Man, you guys are the best. Samantha, TSP, shout out. Okay, so that first integral is going to become 9/8 natural log of x plus 5. I didn't even want to use u sub on there. Typically, when you use partial fractions, it should be that simple. What is the next one, guys? That last integral. This should be plus 1/8. And I have something else. What should that be? It's an x minus 3 on the bottom. Let's go ahead and make it a natural log of x minus 3. All right. Now, am I done or am I missing something? I think I'm done, unless the chat wants to tell me otherwise. Did I forget anything? Or is this it? Ah, Swanson said plus C. That's right. That is right. Nice. Okay. Okay. Samantha, how did I get ln? Let's just talk about that a little further. Okay. Let me just show you why that's the case. I'm going to show this. Actually, let me just shrink this since this is like where we were left off. But if we have this integral, 1 over x plus 3. Okay. Actually, let's just pretend it was a 9/8. Okay. First thing that you want to do is you want to bring the 9/8 on the outside just because it's a constant. So you have 9/8 integral of 1 over x plus 3 dx. And then what I'm really doing, because this answer is pretty simple, u was equal to x plus 3. So then du is just equal to dx. And then so now you have 9/8 integral of 1 over u times du. And this integral here is a very fundamental integral that's just equal to natural log of u. Or it's not just natural log of u, but it's equal to natural log of absolute value of u. And then, of course, I have the plus c. So where did I get that natural log? I technically did u sub, and then it rewrote as a 1 over u. And that is a fundamental integral. That 1 over u is just going to equal to natural log of u. And so now I just plugged it back in. 9/8 natural log of x plus 3 plus c. So that's why I didn't want to show that work, because typically in calculus you see this, you're like, oh, okay, that's pretty, you can see that right away. You can do sub in your head, or you kind of know that that's just what it turns to. Hopefully you do take calc soon, but you're welcome. Okay, so this is, since people, I love every time people are talking in the chat, I kind of I get ideas, and I want to do a synthetic division problem and another one for someone talked about long division. It was Gabriella or someone else messaged it. Rotational volume. We can do that too. Okay, but let's go ahead and talk about one real quick, and then Brandon, I will talk about a volume problem later on. So let's go ahead and do this problem. Integral of x cubed plus 6x squared minus 5x plus 1 all over x plus 6. So who was it that said? Oh, Varis. Yes, Varis said long division. So we technically are going to do long division. Okay? We are going to do long division, but then in honor of, who said it? Was it Gabriella? Yes, we're going to go ahead and use synthetic division here. So long division or synthetic division is long division. It's just a special case of it. And why is because we have that x plus 6. It's a simple linear binomial. So we're going to go ahead and use some long division. As you can see, the degree of the top is more than the bottom, so we can easily divide that. So synthetic, here we go. We're going to put the constants of the top, or not just the constants, but the coefficients. So we're going to start off with 1, 6, -5, and 1. What do I put on the outside? Do I put a 6, or do I put a -6? Thanks, Yusuf. I'm just here to talk math with you guys. -6 on the outside, that's for sure. -6. So every time you use synthetic division, we are going to have to do the opposite value of that binomial that we have in the bottom. And so now we just continue with our synthetic division. We drop down the 1. We multiply by the -6, which is -6. -6 plus -6 is, or I'm sorry, +6 times -6 is going to be 0. And then we multiply again. That's going to be 0. -5 plus 0 is -5. -6 times -5 is going to be 30. And we add this together, it's going to be 31. Okay, so we have a remainder, but that's okay. So now we have integral of x squared plus 0x. I'm just going to actually write that. Minus 5 plus 31 over x plus 6 dx. TikToker, this is going to be calculus. And as I'm going to simplify this, Samantha, this is for you. That last integral, 31 over x plus 6, we should know what that is now. So let me just rewrite this. We're going to separate this in two. It looks like 3 different integrals. So we have integral of x squared minus integral of 5 dx plus integral of 31 over x plus 6 dx. All right. We're doing this for Samantha because Samantha was really curious about that last integral, and we're going to go ahead and solve it. Samantha, if you're still here, we'll love to know what you think the answer is to that. Okay, so the first one, we're just going to implement power rule. X cubed over 3 minus 5x plus, here we go, 31 natural log of x plus 6, and then plus c. That's it, guys. So it's really nice. You see some crazy polynomials, but all you have to remember is long division or synthetic division. That's it. Okay? And then from there, hopefully you know your algebra, or you are pretty proficient in your algebra skills. If you're taking a calc class, you definitely should be. And then we just simplify it, take it one step at a time. Okay. Someone was talking about rotations. So I feel like we should do that. Wait, before we even continue, this is a really interesting one that we can do. Integral of x cubed x to the 5th, e to the x cubed dx. Where were you getting those notifications from? Yeah, that's interesting. I'm so curious about how you guys handle that, because when I was in high school, we hardly had phones. I don't think an iPhone came out till I almost graduated college. So I'm curious how teachers handle people having phones. I mean, you can't avoid it. Everyone has a phone now, an iPhone or any smartphone. So I could imagine it'd be frustrating for both students and teachers. All right, guys, looking at this integral here, how should we go about it? Any suggestions? Okay, we can do slicing of, okay, y is equal to root x negative root. Okay, people are having some ideas, I see. This is even easier than that. Oh, by parts, Mr. Walker. Anti-product rule. Ooh. Anti-product. The tab. Ooh, okay. So it seems like an integration of parts. I'm loving these ideas. I'm U sub, okay. Now, the anti-product rule, is that the do the table U sub? Okay. Interesting. This is one of those tricks that U sub and then tabular method after canceling. U sub and then tabular method after canceling. So that means, so you want to make, you know what? I think a lot of people are pushing for U sub. I'm going to do U sub because there's a possibility it could work. I didn't solve it this way, but let's try it. Okay. So that means that U is equal to x cubed du. I'm assuming that's what they mean by U sub. Is going to be 3x squared dx. And so that means du over 3x squared is equal to dx. And then so now we have integral of x to the fifth e to the u times du over 3x squared. Okay, let's be careful here. We have an x to the fifth on the top, which is going to become x cubed because that's going to cancel out with the x squared on the bottom. And then we bring the 3 on the outside. Let's see if this works. So now we have 1/3 x cubed e to the u du. Did I do that right? I think so. Oh, this is pretty neat. And then from there, we just use the idea. We're going to use the idea u is equal to x cubed, and we're going to plug that into our integral. Oh my goodness, I did not see that. I didn't even solve it this way. Yo, this is pretty cool. And then I think from here, we can definitely use the table. So how does the table work? We have the d, the I, and then obviously we're just going to start off with plus, minus, plus, minus. We don't know how far we're going to go. But the d is just going to be the one that we're going to derive or differentiate. Yes, Lance, it worked. I honestly did not think it was going to work. That's pretty cool. So u is our d value. We're going to take the derivative of that, which is 1, and then 0. And then our e to the u is our integral. We're just going to integrate that. That's just e to the u, e to the u. And then we're going to do the tick, tack. I couldn't finish it. There's no toe, but tic-tac-toe, basically. And then so now our answer still has a 1/3 on the front. And then we're going to start off with u e to the u minus e to the u. Ooh, interesting. So I'm going to do two things at the same time here. I'm going to distribute the 1/3. And then I'm going to go ahead and plug in our value for u back into our integral or our solution. And now we have 1/3 x cubed e to the x cubed minus e to the x cubed plus c. Yo, that u sub, it worked. Slant. Oh, so people, you were asking how I did it. So not this method. It's basically the same thing, but I'll show you what I did. I won't work it out, but I'm just going to give you the idea real quick. The way I did it is when we started off in the beginning, we had x to the fifth e to the x cubed. I knew that if I took the derivative of e to the x cubed, it's going to be like 3x squared e to the x cubed. So I'm kind of thinking ahead there. So then what I did is I rewrote my integral to look like this. X cubed times x squared e to the x cubed dx. And then I made this my... I think I made this my u and then this my dv. That's how I did integration by parts. But I just separated that so because I knew I was going to be able to take the derivative of that. Okay, hopefully that made sense. And you still, what you're going to end up doing is you're going to end up doing two integration by parts, but it's basically we just did the table and that was much easier. Okay. So let's try this one. This one was actually one that I was promoting in my recent TikTok about today. I have integral of sine cubed x all over root cosine x dx. All right, curious. Let me know in the chat what you guys think I should make my u, maybe my, I don't know, what method should I use here? Shall we try? Ooh, make sine cubed your u. Okay, let's try it. So someone said, user 712906, said that my u is going to be sine cubed x. Now let's just think about what's going to happen when we do that. du is equal to 3 sine squared x and then cosine x dx. Looks a little more complicated, right? So maybe not. Okay, so we're going to go ahead. I think I believe it was Slants was kind of already pushing ahead with the idea that we should do is we're going to make u equal to cosine x. And then I'll use that idea that you mentioned about the u squared. But user, again, you continue trying u substitution. If it doesn't work, just start back up again, okay? It's okay to start all over. So then our du or our u is equal to cosine x. So our du is negative sine x dx. So then du is equal to negative sine x equal dx. Okay, so then now we have integral of sine cubed x all over root u times, don't forget our dx was du over negative sine x. Here we go. So let's see, one of the sine x cancels out with the 3 that's on top, so that just becomes a sine squared. And I'm going to bring that negative on the outside. So now we have negative integral of sine squared x all over root u du. All right, and then it looks like Slant was already talking about the method that we should use. They said, well, in the very beginning, we had that u was equal to cosine. So why not square both sides and say that u squared is equal to cosine squared? But you can see that doesn't really help us yet because we have sine squared in our integral. But what we could do is we can say, well, we know that cosine squared is 1 minus sine squared. Using that Pythagorean identity. Let's move the 1 to the other side so that we have u squared minus 1 is equal to negative sine squared. Chat, that is exactly what this value is. I'm going to circle that. Maybe I shouldn't have brought the negative on the outside. I should have kept it there. But then now that's really cool because what we're going to have is that negative sine squared is u squared minus 1. I believe Slant was kind of saying that. I might have just rewritten it a little different. But what this is going to become is integral of u squared minus 1 all over. Let me rewrite the root u as u to the 1/2. Yeah, sometimes, listen, some people like the negative, some people don't. I try to avoid them as much as we can, but if you write it down, that's totally fine. But you were on the right track. You did 1 minus u squared. I just did u squared minus 1. Same thing. Okay, what should I do here? I have u squared minus 1 over u to the 1/2 du. Why? Well, I should definitely rewrite this. I only have, rationalize the denominator. Okay. So partial fractions, look at what Gabriela said, okay? They said we're going to go ahead and rationalize the denominator, and I kind of like that idea. But just think about what that's going to happen. You're still going to be left with a root on top, so it does kind of complicate things. But here's an even better thing. But again, I'm not trying to put down your method. I think you should definitely try that next time. But I'm just going to rewrite this as u squared over u to the 1/2 minus u over u to the 1/2 du. The idea about calculus is that we don't like radicals. I will much prefer to not have any radicals whatsoever. So when you're talking about rationalize the denominator, you can just go ahead and rewrite it as u to the power of 1/2. And then so now look at this, guys. We have the first fraction, u squared over u to the 1/2. All we have to do is subtract those powers. So that's going to become u to the 3 halves. And then that second part is just going to be u to the negative 1 half. All I did was just bring the u up. Yeah. But Gabrielle, I love your thinking. You should always try to do that, because if it works for you, then it's going to work. Okay? Some people might say, no, don't ever do that. That's dumb. That's not the case. You do whatever works for you, because that's what your brain is logically going through that process. Okay, so now let's go ahead and use the power rule, and we're going to have u to the 5 halves divided by 5 halves. Don't forget your fractions here. Minus u to the 1 half over 1 half plus c. And then so now we have 2/5 u to the 5 halves minus 2 u to the 1 half plus c. Whoops. Plus c. Such a terrible plus c. Oh, I feel like I had space for the entire thing. But now we're just going to have to shrink this just a tiny bit. Okay, here we go. Last part is just to rewrite our problem back in terms of x. Don't forget that u was equal to cosine x. So this is going to become 2/5. And then cosine x to the power of 5 halves minus 2 cosine x to the power of 5 halves plus c. That's it. A, you're basically, you're exercising your brain. So technically that's a win. So when people tell you, why you're on TikTok all day, you're watching it live, man. You're doing math on TikTok, and that's fine. Yeah, you don't need to be you don't need to be doing that homework. All right, guys, so I have time for one more problem. Let's see. Let's try to make it a good one. Let's go ahead and try. Dun, da, da, da. What should we do? Okay, one that we haven't really quite seen. Slicing. Okay, let's just talk about a slicing real quick. So let's just make this f of x equal to negative x squared plus 6x. Okay, and don't forget that if we're going to do slicing, you really just have to remember the equations for the shapes that we're referring to. So, one of the ones that they love to give you is you're going to find the volume of this shape, volume of shape, and the cross sections, aka the sliding, are half circles. And then they have to specify where that diameter is. And the diameter is going to be perpendicular here to the x-axis. Okay? Well, don't forget, we're doing half circles. So if you were to kind of draw what this half circle will look like, don't forget that what I'm highlighting here on the bottom, that diameter, that is that radius that we have on top. Okay? I will leave you with a heavy, in my opinion, a pretty extensive, not that long, but I'll leave you with a question at the end, okay? So since we're doing the slicing again, you just have to remember this is a shape. Well, this is a half circle. If we're talking about a half circle, don't forget that the area for that is pi halves r squared, or pi r squared divided by 2. But then our radius is equal to the diameter divided by 2 squared. I'm talking about the diameter because that's exactly what we need to find. The diameter is going to be our function, or the length of the function. And so now we have pi over 8 d squared. How did I get pi over 8? Look at that. I still have the 2 from the bottom, and then when I squared the 2 that's inside the parentheses, that becomes a 4. So 4 times 2 is going to be 8. So now really when we're trying to find the volume, that's just the volume from 0 to 6, pi over 8 on the outside, and then d squared dx. But remember, our d is going to be that shape. Our d is that radius in our function. By the way, I knew it was 0 to 6 already just because this is like one of my favorite functions to use when we're trying to explain this. But you would definitely want to set the equation equal to 0 and find when those values cross the x-axis. Well, now our d, don't forget, is that entire function. So we have volume is equal to pi over 8 from 0 to 6 of negative x squared plus 6x to the power of 2 dx. And then from there, you just have to use the FOIL method to simplify this. This will become x to the 4th minus 12x cubed plus 36x squared. And then you just use the first fundamental theorem of calculus. You're just going to go ahead and integrate this and then plug in the 6, plug in the 0, and then you get your answer. Okay, we can definitely talk about cross sections later on. Maybe I'll talk about that on Thursday because I think that's a common question that I've been seeing. Okay, so I am going to leave in a few minutes, but let me just leave you with 2 problems to do on your own, and then we can talk about it. If you feel like you got the answer, comment on one of my videos to say, hey, I got the answer to that one problem that you posted at the end, and then we can discuss later on. So let me leave you with 3. You guys can take screenshots of these. This was one problem. This was another. And then this was one of my favorites. And again, this is just a bonus. I think I got the answer to this one. A really unique problem. But that integral of 1 over x to the 5th plus 1. Hassan, no, it's Miguel. Oh, yeah, for sure. It's Yusuf. It's so much easier because it's only one function. It gets much more difficult later on. But I just kind of want to do, a quick introduction to that. But we can talk about that on Thursday. Thursdays, I'm on here same time. Fridays, I am on here around the same time. We're doing off-trail math, so really, it could be anything. Last time I was doing the Feynman technique. I was doing the Weierstrass substitution when it came to integration. And I always just kind of look over the chat and see what you guys want to cover, and that's what we do. Mondays, I am live on YouTube in the morning, 10 a.m. my time. That's Pacific Standard Time. But yeah. Anyway, guys, I hope you guys like this live. Please like the live. We're so close to almost having 20K here on TikTok, so please follow me if you can. Follow me on Instagram as well, and subscribe to my YouTube channel. But again, I'm here every Tuesday, Thursday, and Friday on TikTok, 3 p.m. Hope you guys have a great rest of your Tuesday. I will see you all very soon. All right, everyone, take it easy. Bye now.